Okay, let's just dive right into a metallurgical mystery today. Welcome to this explainer. We're going to unpack the actual science behind a material you literally interact with every single day. I'm talking about the backbone of modern engineering, architecture, and, even the forks in your kitchen drawer, stainless steel. We see it everywhere, right? And we completely trust it. But as we're about to discover, there's this hidden, microscopic world at play that completely flips everything we thought we knew about this supposedly indestructible material.
So we all grew up believing this universal myth. Does stainless steel really not rust? I mean, the very name kind of implies it's absolutely immune to the elements, right? It's supposed to be that ultimate metal, the one you pick when you absolutely positively cannot afford your parts to degrade. We just expect it to stay pristine forever. But is that actually scientifically accurate? Or is it just really clever marketing that's totally blinded us to the reality?
Section 1. The hidden truth of stainless steel. You'd be amazed, seriously amazed, at how many seasoned engineers have stared in complete disbelief at a ruined piece of equipment, just scratching their heads asking, how in the world did this happen? I use stainless. Well, the shocking reality here is that this seemingly invincible metal actually can and does suffer from severe concentrated corrosion under specific conditions. Yeah, it is not immune, and when it fails, it doesn't always happen slowly. It can rot away in a highly concentrated, devastating way. Understanding that this metal is vulnerable, that's the absolute first step to actually protecting it. Its strength is conditional, not absolute. Enter our main villain, Crevice Corrosion. This is an invisible threat you absolutely have to understand if you want to stop your metal from failing. In the engineering world, this bad boy accounts for a massive chunk of all stainless steel failures globally. And the crazy part, it doesn't happen out in the open where you can spot it. Oh no, it's a silent killer that specifically targets those microscopic gaps, tight corners, and trapped spaces in your assemblies.
Section 2. The paradox of the 3 corrosion factors. So, to fight this villain, we kind of need to know the usual suspects, right? Typically, we blame 3 primary factors for destroying metals. First up, oxygen, a super famous oxidizer. Then we have chloride ions, like the salt in seawater, which aggressively break down surfaces. And finally, hydrogen ions found in acidic environments, which basically just eat away at the material. These are your classic, everyday chemical bad guys. Now here is where it gets really weird. The incredible paradox is this. Oxygen is a known destroyer of metals, sure, but starving stainless steel of oxygen is exactly what kills it. I really want you to let that sink in for a second. Oxygen is literally on the list of things that cause corrosion, but if you take oxygen away from stainless steel, it corrodes incredibly fast. It's a total mind-bending contradiction. The very thing that usually destroys metal is the exact thing stainless steel desperately needs to stay alive.
Section 3. The reversal of iron and chromium.
To wrap our heads around this bizarre dependency, let's look at the core recipe. Stainless steel is an alloy, right? It's a blend of different metals. Now, if we pit its 2 main components against each other, a pure block of iron versus a pure block of chromium, which one do you think would survive the elements longer before rusting away? Common sense tells us chromium, of course. I mean, it's the magic ingredient in stainless steel, so it must be the tougher of the 2, wouldn't you think?
Well, check this out. The standard electrode potentials show us a shocking truth. Iron is actually about twice as resistant to corrosion as chromium. Crazy, right? In electrochemistry, a higher potential means better resistance. Iron sits right around negative 0.41 volts, while chromium is all the way down at negative 0.734 volts. Basically, inherently, on its very own, chromium is vastly weaker and way more prone to corrosion than basic everyday iron.
Which brings up a huge question. Why on earth would engineers deliberately take a much weaker metal and add it in to create a supposedly rust-proof alloy? It sounds like terrible logic. Why take perfectly good iron and mix in a metal that fundamentally wants to corrode? It kind of feels like we're setting the whole thing up for failure right out of the gate, doesn't it?
Moving on to Section 4. The film A Breathing Shield.
The answer actually lies in this miraculous microscopic transformation. What engineers figured out is that chromium has a secret weapon. When you combine that inherently weak chromium with oxygen, bam, it creates a powerful force field. Specifically, a microscopically thin, completely invisible film of chromium oxide right across its surface. This film acts as an impenetrable shield. But remember that paradox we just talked about? That shield requires oxygen to form. The exact moment that chromium meets oxygen, its protective potential skyrockets by an astonishing plus 1.33 volts. It goes from a weak, highly vulnerable metal way down at negative 0.734 volts and just shoots up the scale. We're not talking about a minor improvement here. This is a massive, transformative chemical leap that completely redefines how durable the metal is.
To put that into perspective, that massive jump brings our previously weak chromium incredibly close to the corrosion resistance of pure gold, which sits right at plus 1.5 volts. And pure gold is famously known for never tarnishing or rusting. By simply allowing chromium to interact with abundant oxygen, we literally create a shield that rivals one of the most noble, unreactive metals on the entire planet. And that is exactly why stainless steel works.
But here's the catch. This shield isn't static. It's actually a lot like a living organism. It requires a continuous supply of oxygen to keep rebuilding. If you were to look at this film under a super powerful microscope, you'd see a highly dynamic environment. The film is constantly breaking down, melting away, and then immediately reprecipitating, basically healing itself over and over again. This self-healing property is absolutely incredible, but it relies 100% on a non-stop continuous supply of fresh air to patch up the broken parts of the shield.
Section 5. Crevice corrosion, and what happens when oxygen is blocked.
So let's bring it back to the real world. Simply holding a bolt tightly in your hand, trapping water in a tiny microgap, or getting barnacles stuck on the surface. All of those physically block the massive amount of oxygen that living shield needs to survive. When you assemble two pieces of stainless steel, the microscopic gap between them stops oxygen from flowing freely. If a barnacle sticks to a boat hull, boom, tight seal. Even just resting a piece of rubber against the metal can literally starve it of the air it so desperately needs.
And here is the fatal flaw of a crevice. It lets in just enough water and oxygen to kick off the rusting process, but not nearly enough to fuel that self-healing cycle we talked about. Moisture seeps into these microgaps, right? And water carries tiny trace amounts of oxygen. Now remember our list of chemical bad guys? Oxygen causes rust. So that trace oxygen attacks the metal. But because the gap is so tight, there's just no fresh oxygen flowing in to rebuild the protective shield. It's a literal trap.
So once that living shield suffocates and dies, the metal immediately reverts back to its naturally weak state, and it corrodes violently and locally. The whole illusion is just shattered. Without that breathing shield, the stainless steel drops right back down to that terrible negative 0.734 voltage. It becomes fundamentally weaker than plain old iron, and it begins to rot aggressively from the inside out, right there inside that hidden crevice.
Section 6. The crucial key to preventing crevice corrosion.
So what should you actually take away from all this to prevent your materials from failing? Well, we've learned that stainless steel isn't magic, right? It's a dynamic chemical reaction that demands a very specific environment. And the ultimate solution is beautifully, elegantly simple. Avoid tight crevices and give your stainless steel an abundant, continuous supply of oxygen. Don't seal it up tightly where water can get trapped. If you have to use joints, make sure they're fully welded and ground completely smooth so no microgaps exist. Or just design it for free airflow and drainage. Let the metal breathe and it will protect itself indefinitely.
As we wrap up this explainer, I want to leave you with a thought to consider the next time you rely on a piece of stainless steel. Think about the infrastructure all around you, the boats in the marina, or even the appliances sitting right there in your home. Are they truly safe? Or is there a microscopic gap somewhere, slowly starving the metal of the oxygen it needs to survive? It's a pretty powerful reminder that sometimes the absolute best way to protect a strong material is simply to give it some room to breathe. Thanks for exploring this fascinating metallurgical mystery with me.